All right, let's take a look on page 162. On Friday, we were practicing these kind of more involved derivatives where we may have to use more than one shortcut. I think it was going fairly well. We got really good with identifying which main one we had to use, but then in the process, we may have had to use an additional one. We're going to take a look at a few of those today, but in terms of graphs and tables, okay, how we can use those representations to help us find particular values. So at the bottom of page 162, it says, given the graph of h of x, find the equation of the tangent line to the graph of p, and p is specifically described as the square root of h. So in other words, if you were to take the square root of all of these values, you would get a new graph, and that would represent p of x. And we're looking at the location of -4. So it's like, I know it's like beating a dead horse, but what do you need to know to write the equation of a line? A point and a slope. Okay, so maybe we'll tackle the point first. If we were to plug in -4 into the p equation, that would look like the square root of h of -4. Okay, we're plugging in -4 for the x value. Can we figure out what h of -4 is? They give us the graph of h.
4.
It'd be 4, yep. If you plug in -4, you get out 4. So in other words, our point value would be 2 after we take the square root of that. Okay, so there's our point. We then have to figure out the slope, but the slope comes from the derivative. So let's go ahead and tackle the derivative of p. Hopefully we're getting into the habit of whenever we see a root, we rewrite it as a power. So if you were to rewrite the original equation, it would be h to the 1/2. So in order to find the derivative, you got to think about your shortcuts. Okay, which one are you going to use? Product rule, quotient rule, chain rule, the generic power rule. How can you determine that? Let's see, product means multiplication. Are we multiplying anything together? Not really. Quotient means division. Are we dividing anything? Definitely not. We got a chain. Yep, we have an outside value or piece, and we have an inside value of piece. That's the whole composite idea, putting one function inside of another. So for chain rule, we got to think about those onions or gobstoppers, taking one derivative, one layer at a time. So the outer layer is a power of 1/2. To figure out the derivative of a power, we're going to utilize that power rule. So we would bring down the 1/2. Our new power, after we subtract 1, would be -1/2. But as we peel back that outer layer, we still have the inner layer left, which would just be the h of x. All right, so we got to finish our chain rule. We got to keep peeling back these layers. If you peel back the power of 1/2 from the original equation, you still have h of x. So let's find the derivative of that layer. How would you represent the derivative of h of x? H prime. Okay, and we're going to multiply that. You keep multiplying each derivative layer. All right, maybe we can clean this up. Everything's being multiplied together, and notice how we have a negative power, so we can move that to the bottom of a fraction. We already have a 2 in the bottom of a fraction from the 1/2 out front. So when we move the 1/2 power to the bottom, maybe you want to rewrite it as a square root. If you want to reconvert it, that's okay. The 1 and the h prime, though, are going to remain in the numerator. So whenever you're cleaning up a chain rule, since everything's being multiplied together, it's either moving to the top of a fraction or a bottom of a fraction, depending if the power is positive or negative. Okay, so there's our derivative. Let's go ahead and plug in -4 to see what we get. So we need h prime of -4 over 2 times the square root of h of -4. All right, so h prime of -4, the derivative of h, the slope of the tangent line on the h graph, specifically at -4. So there's that -4 spot again that we found previously. If you were to draw a tangent line that followed the path of the graph, what would the slope of that tangent line be? Can we pick 2 really good points and find the slope? Let's see, the slope of that line looks like -1/2. Down 1, right 2, okay. So that's the derivative value. Down below, we already said the point value was 4. Okay, so we can rewrite that. And simplifying, we'll have 2 times 2, which is 4. -1/2 divided by 4, we got -1/8. So there's our slope. All right, so we found the point, we found the slope, utilizing the derivative. We're going to put it together to write our equation. Let's see, y minus 2 equals -1/8 x plus 4. We doing okay with a graphical example? Okay, let's go ahead and tackle maybe a table. So instead of looking at a picture, we got to look at some values. All right, let f of x and g of x be differentiable. That just means a derivative exists. Okay, there's a slope of a tangent line at a spot. And we have all these different values from the original functions and their derivatives. Let's see where we can go from here. Is the graph of h, which is defined by this combination of f and g, is it increasing, decreasing, or at a max or a minimum at this spot? What do you think we should analyze to help us answer that question? Is the graph increasing, decreasing, max, or min? Well, if we take a look at the x value of 3, okay, the y value at that spot on the f graph is -5. So that just means that the f graph is below the x-axis because your y value is negative. For the g graph, though, your y value is 4, which means the g graph is above the x-axis. That doesn't really tell us if we're increasing, decreasing at a max or a min. That's just giving us a location. What should we be looking for the behavior of the graph? Going up, going down, yeah. A derivative, okay? If a derivative is positive, the original graph is increasing. If it's negative, we're decreasing. Remember those connections? Okay, so increasing, decreasing, max, and min, those are kind of like key words there to analyze a derivative, okay, a slope of a tangent line. So let's go ahead and tackle the derivative of h. So you got to ask yourself, take a look at that h equation, which derivative shortcut or shortcuts, because you might have to use more than one sometimes, would you want to use? Are you multiplying things together? Are you dividing things together? Do you have inside and outside pieces? What do you want to try? It's a chain. We have inside, outside. Yes, this kind of looks like multiplication because I know there's parentheses in there and you guys are used to parentheses mean multiplication. But if this was multiplication, it would look more like f of x times g of x. Okay, they would actually show you that you're multiplying. This is a chain, though, because you have an inside of G and an outside of F. So let's go ahead and peel back those layers. The outer layer is F, so we would represent the derivative of that layer to be F prime. If we peel back that layer, though, we still have the remaining layers that were on the inside. So we'll just rewrite G of X. So since you peeled back the F layer from the original problem, what would be the derivative of the next layer? How can we represent the derivative of G of X? G prime. So we're going to multiply that derivative layer. So you peeled back F, okay, you found the derivative of that. Then you peeled back G of X, which is kind of the end of your equation because you only had two layers. You had an outside and an inside section. So that's it. So let's go ahead and plug in 3 into this derivative because it's asking us at that spot, okay, not really anywhere else. At that spot, how is the graph behaving? All right, so based off the table, we should be able to fill in some of these values. G of 3 was 4. G prime of 3 is 6. However, we also have to find F prime of 4, which looks like 8. So 8 times 6, we got 48. So based off that value, okay, are we increasing, decreasing, at a max, at a min? How do you know? Justify your answer. What do you think, Braden?
H of X is increasing at X equals 3 because H prime X is positive.
There we go. H of X is increasing specifically at this location of 3 because we were just checking that spot. You could check other ones, okay, but we're just checking this one because the derivative is positive. Okay, we would still have the same answer the same reasoning and justification even if this 48 was 1. Okay, it doesn't really matter what the number is, you're just looking at the sign. The number is kind of telling you the steepness. Okay, is it a very steep increase or a very steep decrease? Now 48 is a very steep slope. Could you imagine walking up 48 and then over 1 unit? Okay, so it's increasing fairly quickly at that spot because you have a steep slope, but regardless it would still be increasing. We remember those connections? Okay, so increasing, decreasing, max or min, kind of clues that mean derivative. You got to check out what the derivative is doing. Let's check out the next one. If p of x is this equation, what is the derivative of p at 1? Okay, so let's tackle the derivative. Taking a look at your equation, what shortcuts do you notice? Multiplying, dividing, inside, outside. What's going on? I see pencils moving. You're trying something. We got a chain, okay? We have an outside of G, an inside of 2x. Outside, inside, we have those layers, okay? So the outside layer is G. If we were to take the derivative of that layer, we would say G prime. And we're left with the other layer, okay, after we peel that one back. So you just peeled back or found the derivative of G. Now you got to multiply by the derivative of the next layer. The derivative of 2x would just be 2. Okay? So you only have 2 layers that time. Really nice short chain rule. If that's the derivative, let's go ahead and plug in 1 and see what we get. So based off the table, G prime of 2 is -1. So overall, we get -2. I know it's not asking you this, but if it went on to say describe the behavior at P of the P equation at this spot of 1, what would you say? What's the graph doing? Decreasing, right. Notice how the derivative was negative. Okay, so there are a bunch of other things that could be asked from that point. We doing okay? Table so far? So good? Alright, let's take a look at a good one. If q of x is that equation, what is the value of the derivative at 4? What does this say about the graph? Okay, so we have a two-parter here. Hopefully we can rewrite this. Okay, always change a root to a power. Power of a half. Alright, so think about shortcuts. What do you want to try to figure out the derivative? Are we multiplying things together, dividing things together, inside, outside pieces? What do you see?
Chain.
We got another chain. We got inside, outside. Yep. This time outside, though, is a power. Okay, not a function like in the other two. So derivative of a power, we're going to use our power rule. We're going to bring down the 1/2. Our new power after we subtract 1 is -1/2. And if we peel back that outer layer, we still have the inner layer, or the next layer left on the inside. So let's go ahead and multiply by the derivative of that layer, okay, whatever it might be. So if you peel back the 1/2 power from the original equation, you then have f of x plus g of x. So let's just go ahead and work our way through the derivative. How would you represent the derivative of f? F prime, okay, and then we're going to add the derivative of g, which would just be g prime. Okay. So it looks like we're done. We took the derivative of the outer layer, we then took the derivative of the inner layer, and that's all that we had left. So let's see. If we were to clean it up, okay, everything's being multiplied together, so it's either moving to the top or a bottom of a fraction, depending if the power is positive or negative. We could put the 2 from the 1/2 in the denominator. The first parenthesis group all has a negative power, so it's going to move to the bottom. And since the power is a half, maybe you want to reconvert it to a root. The other quantity that's being multiplied, okay, the derivative of that inside layer has a positive power, okay, of a 1. So all of that would be left up top. So there's our little cleaned up derivative. So they want us to plug in 4 and see what we get, and based off that number, describe the behavior of Q. Alright, so based off the table at the top, I know it's not on the board, but it's on your paper. F prime of 4 looks like 8. G prime of 4, we got -2. F of 4, we got 1. And G of 4, we have 7. So it looks like we have 6/2 square roots of 8. Or simplified to 3 square root of 8. Alright, so there's Q of 4. That was like question part 1. Question part 2, what does this number, what does 3 square root of 8 say about the graph of Q? Specifically at this x location of 4 that we plugged in. It's increasing. All right, so Q of x is increasing at this x equals 4 spot. How'd you know? Because Q prime, okay, the derivative is positive. Perfect. Not too bad? They're kind of thinkers, they can get there. I want to try one at the bottom of that page real quick, okay? We're going to take this equation from the last one we just did, and I'm going to change one little thing, okay? So this is going to be like an extra example. What if q of x was the square root of f of x times g of x? Okay, instead of the addition, like the problem was before, what if I changed it to multiplication? How would you find the derivative in this case? Remember, you can rewrite a root as a power, so if you want to go ahead and rewrite that, we can. What are some derivative shortcuts if this was the equation? Do you notice any? Are we multiplying things together? Are we dividing things together? Do we have inside, outside pieces? Chain first. Okay, if you say first, that means we got to do something else. And then product. Okay, so notice how we do still have outside, inside pieces. Okay, so definitely chain. But the inside piece happens to be a product. You're multiplying two things together. Notice how the chain rule, though, is the more applicable one, okay, the more present one, because that encompasses the entire equation, okay? The product rule only affects the inside, okay, not necessarily the entire thing. So we're going to start with chain, but in that process, we may have to do product. Okay, let's try it. So the derivative of a power, we can bring that down. Our new power would be 1 less. Okay, so we peeled back the outer layer, we found that derivative. We still have the inner layer left. So now we're going to multiply by the derivative of the inner layer, which we said was a product rule. What's our phrase for product rule? Do you remember it?
1d2.
All right, so our first function is f, d2